Okay, let's get started. Good evening and welcome to the week 6 live session. Hope you can hear me and see my screen clearly. Okay, I'll assume that's a yes. And so we had, I think, a couple of questions from last week. So we'll start off by finishing that, move to this week's recap, and then move to the questions for week 6. And if you have any doubts in week 6 course content, please post on chat anytime. I'll take them up either in the end of this session or in the next session, depending on how much time and how much content I need to get for your questions. And on the discussion forum this week, I think I saw some questions around assignments, which I think the TAs have answered. I also saw something around the codes discussed in class, which also they are the right people to ask. So I think I will not be addressing any of those questions in this session. If you have any other doubts regarding the course content itself, feel free to ask here. So let's get started. Okay, so we are back to the divergence, the warp divergence part. I think we had one question around that we didn't do last week. So consider a GPU architecture where the warp size is 16 and a kernel program which is launched with a configuration where the total number of threads in a thread block is 32. Consider the following conditional statements in the kernel: tid.x less than 16, mod 16, mod 32, and tid.x divided by 2 greater than 0. Which of the following operations or statements is correct? All conditional branches are divergent. Conditional branches 1, 2, and 3 are not divergent. 2 and 4 are divergent, and 1 is divergent. So I'll go back to this part and then we can come to the options. You can take a couple of minutes to solve this. And then we'll discuss the answer. So by now I hope the warp divergence part is clear. If not, again, you can let me know on chat and we'll go over it in the next week a little more. Okay, I'll move over to the options and give you a minute more. If you have an answer, you can let me know. So again, quick recap: when you have questions on divergence, it basically means whether threads in a warp are diverging or are taking different branches of the conditional statement. So if you have a particular conditional statement with a simple two-way branch, if some threads in the warp take this branch and some take this, it's said to be divergent. Okay, we have one answer saying D. Okay. Anyone else? D. Okay. Wait a few more seconds. Anyone else? Okay, if not, let's look at the answer. The answer is C. 2 and 4 are divergent. So let's again see why it's C and not D, since some of you thought it's D. So now warp size is 16 and number of threads in the thread block is 32. So you'd have 0 to 15 and 16 to 31. So the D option was TID dot x divided by 2 greater than 0, and the official answer from NPTEL says 2 and 4 are divergent. So let's look at 2 and 4, right? So 2 is tidx dot x mod 16, and this one is divided by 2 greater than 0. Now can someone tell me what happens to 2? Is it divergent? If so, why is it divergent? Since we solved a few of these questions last week, this week I expect all of you to kind of do this on your own. So we'll discuss the answer, but we'll first see if you're able to come up with the answer yourself. So what happens in the modulus case, for instance? So is 1 really divergent? I think all of you said D, which was 1 is divergent. So TID dot x less than 16, 0 to 15 is less than 16, and 16 to 31 is not. So both the warps take two different branches, but within a warp there is no divergence. So is it clear why 1 is not the right answer at least? This option is not divergent basically, and I think all of you said this. Okay, that much is clear. Now try out the same thing with the other three options offline, right? Since we have already solved 3 or 4 questions in this model, I don't want to spend too much time on it. What you'll need to do is come up with the thread IDs for each warp. You're given the warp size, you're also given the thread block size. So you'll basically have 2 warps in this question, and the thread IDs will be like this. What you need to do is evaluate these conditions on both those warps and see if threads in a given warp are taking different branches. That's all it is. So this one I've explained. Try it out for the 3 yourself and then see if you're able to come to this option that was given, C. If not, you can let me know, and maybe in the break you can take time to solve this, or even in the next, anytime you solve it. If you're not able to get to C, you can let me know and we'll discuss it again. If not, we'll move to the next question. Consider a kernel processing a 2D matrix of dimensions 2048 into 2048, where each thread is assigned to perform an operation on a single element of the matrix. The kernel is launched with the following grid and block configurations: A32 to 64B2. What are the values of A and B? Select the correct operation. Again, this is, I think, not week 5 exactly. It's one of the earlier weeks, but again, every week there are some of those questions which test your concepts from earlier weeks, just as a sort of revision. This should be easy. Again, we've solved many questions like this. take a couple of minutes to solve it and we'll discuss. Okay, we have one answer A. Okay, anyone else? Okay, we have an answer C. Okay. Any other answers? Not, we'll discuss the answer. So the answer is A, 32, and B is 16. So again, a quick recap was here every thread works on one element of the matrix. So how many elements do you have? 2048 into 2048. That's one side of your equation. Since each thread works on one element, the number of threads is also equal to this itself. Now the number of threads is the product of these 6 terms, right? Because this is your launch parameters, and if you go back to week 3 or 4, you'll understand how this is. So by multiplying all of these 6 values, you should basically get this 2048 into 2048. Now if you try out all these 3 options, you will find out that only A kind of evaluates to that. So that from A, B and C, A is the only one that can be the right answer. Now in week 3 or 4, so this is the official answer key from NPTEL. Week 3 or 4, I think there were some questions which explicitly stated that the maximum number of threads per thread block can be 1024 or can be 2048 or something like that, right? In those cases, there is a bit of ambiguity here, because I think if you evaluate option A, 64 into 2 into 16, you would get 2048. So in case you think of it as 1024, then you could possibly say none of the above as well, right? So if the question explicitly states those limits, it's very clear that you have to check additionally for that as well, apart from just the product of all 6 and the number of elements. But in cases where it's not explicitly stated, it is a bit ambiguous. You can still check for it, and if you say none of the above, if I were evaluating it and you tell me that I said none of the above because the maximum is 1024, that should be fine. But this is the official answer key given by NPTEL for this question, which doesn't seem to take into account that thing. So keep in mind this thing. So when you get questions, be careful about checking for assumptions, whether they're explicitly stated. In the case that there was no none of the above and there was a 4th option which did not match this, again it would be very easy. You could just pick A and say that none of the other options anyway made sense. But in cases where none of the above is there, gets a little more tricky. But anyway, I am sticking to whatever answer NPTEL has provided here. So yeah, hope this is clear. Okay, great. So I think these were the only two questions we had left from last week. So in week 6, broadly, question 10, week 5. Is that an assignment question? If so, is the assignment deadline over and are the answer keys released? Okay. Okay, I'll take a look at it. I don't. We can discuss anything that the deadline is over. So I'll note this down and we can look at it next week. Any other doubts like that before we go into the recap? Anyone who's not understanding certain questions, either in the assignment or just general doubts, please leave a message on chat. I'll give you 30 seconds before we move on to the next thing. Okay, if there's nothing else, we'll keep moving forward. But any doubts that you have, please bring it up, because again, I have dedicated time for that. So if there are no questions, we'll always end early. But if you have doubts, that's always utilizing the time well, right? I'm happy to answer any doubts that you have. So think about it, and even in the break, you can use to quickly look through your notes, etc., to see if you have any other doubts. So this week 6, you may have found it a little complicated because it goes into the details of memory accesses and how these accesses are coalesced and what types of access there is. So you may have found it a little difficult, but again, what I would suggest in case you found it difficult is to separate out the key ideas from the actual code discussed, right? So for instance, the what you are trying to do in those examples, for instance transpose or something like that, may itself bring in some complexities because of the problem, but the ideas that those examples are used to illustrate may actually not be that complicated. So what I would say is, it's okay if you don't understand the code entirely when you watch the lectures, because if you write that code by yourself and you execute it, then you'll probably get a better idea. But from the lectures, when you watch them, try to understand the memory access part of it, right? Given an expression, how is the memory going to be accessed? Because I've looked at the assignment questions for this week, and most of the questions focus on that rather than a particular piece of code and how you would come up with that, right, for a given example. So the memory access itself is more important than a particular example where you're doing something. That's what I would say. So try to separate that out and then understand. So did people find week 6 difficult, or was it very easy, just to get a sense of things? Any answers? Was it very straightforward? Was it very difficult to understand? And I think the number of lectures increased also. If I had maybe 7, 8 lectures as compared to 3 to 4 in the previous weeks. Yes, I understand. Yeah, so yeah, that's what I think. From this week onwards, like, I think 6, 7, 8 will probably be like that. Yeah, assignment questions are not linked directly. Yeah, that's what I'm saying. So the kind of examples that you are given are intended to, they're just intended to clarify those concepts, but the explaining the examples itself takes a lot of time, right? Without that, the instructor may not be able to explain these concepts. So there's a lot of time spent in understanding a particular example, but your assignment questions may not involve that example, because then they have to go into providing that code, etc., etc. So that's what in this week particularly I would recommend If you haven't understood it yet, try out the assignment and then rewatch it from the perspective of just understanding the memory access, right? Every lecture would focus on, so given a code, given a statement, how is the memory access working? So we'll see some questions today also, and hopefully after that you will get a better understanding. If not, you can also ask me what topics particularly are not clear, and we can go through that also. But let's start with doing a very quick recap. So that's one of the reasons why I don't go into the examples in detail even in the recap, because what you need is conceptual understanding rather than full code level understanding. So yeah. So again, just a quick recap. So you have global memory, which is costlier to access, and then you have the whole grid, and within it you have blocks and you have threads, and registers are again very fast to access, and then you have shared memory. There's also L1, L2, and you have this partitioning between the L1 and L1 and the shared memory, right? The 1648 versus 4816. So that's your overall high level memory hierarchy. So now different memory access types are register access, again very fast, then shared memory, and again remember what can access, right? Registers are local to one thread. So if you see this diagram, you'll see that registers correspond to threads. If you see shared memory, you will see that it's corresponds to threads in a block. So it's a block level thing, right? You can see one shared memory per block. Then if you look at global memory, it's accessible by all threads, but it's the slowest. It's basically your RAM, right? So these are the different access types, and the latency of access would differ this way, as in global memory is the slowest, then shared memory is fast, and registers are the fastest. Now when you have warps, so you already understand what warps are, and when these warps request something from memory, the GPU tries to coalesce these global loads. It's basically an optimization, right? So all global memory loads and stores requested by a warp of threads are coalesced, or they are optimized into global memory transactions. So a warp typically requests 32 aligned 4-byte words in one global memory transaction. Reducing the number of global memory transactions by warps is one of the keys for optimizing execution time. Therefore, you need to design efficient memory access expressions. So again, so remember, quick recap, a warp is this group of threads and they all execute in lockstep, right? So, and typically they request, one single warp requests 32 aligned 4-byte words. Again, there is this notion of alignment that you will find throughout computer architecture, right? So you saw those diagrams of memory where if you have an offset, then instead of accessing one row, you end up accessing two rows, and which becomes two transactions, right? So that's this notion of alignment. So what we are trying to do, see, this global memory access is kind of expensive, right? So the more you optimize this, the faster your program will be. It's as simple as that. So you want to reduce the number of global memory transactions by warps. And this is all, remember, this is all at the granularity of warps. Why? Again, because warps execute in sync, right? So we want to reduce the number of transactions per warp, and that way globally also across all warps, the number of transactions would reduce. So that's the aim of all of this. On a tangential note, you had this small section on profiling. So you can profile using this CUDA event API. So CUDA events are of this type, and you can either create an event or destroy an event using these API calls. You can record timestamps using CUDA event record, and if you want the time elapsed between two recorded events, you can do this using CUDA event elapse time. So some of you who have done some profiling on the CPU side would, especially in Python, you would have noticed something like time.time, right? So you might wonder, why do I need these new primitives now? Can I not use time.time? So there are some complexities which come in, because if you remember, we had this notion of a host and a GPU, right? A device. So when you do time.time and things like that, which are non-CUDA primitives, they measure things at the host, right? Let's say this is host and this is device. So if you write host code and you measure, you put a time.time in some section of the code, let's say this part of it, what happens is there may be a kernel launch that happens here, but that is asynchronous, as in that kernel launch that call will immediately return the moment it sends work to the GPU. But you actually, and on the GPU, it may be taking, let's say this is the time axis, right? This y axis that I'm using here. So on the CPU, the call immediately returns, so maybe I get 10 milliseconds. But on the GPU, this call is still executing, so it may take maybe 30 milliseconds. So if I just use a non-CUDA aware or a CPU library to do this profiling, I may end up with wrong timestamps. You'll notice that even in things like deep learning frameworks like PyTorch, people don't recommend using time.time. They will tell you to use something like this, right? CUDA event. So that's because of this. If you measure at the host side, because of this asynchronous nature of kernel launches and returns, you may end up measuring the wrong time. That's why you'll see all of these are CUDA calls. This is just an aside, but in case you're curious. And NVIDIA also has a utility called NVProf. I think the NVProf is fairly old. Now I think NVIDIA has what they call Nsight, is their set of profiling utilities. At a system-wide level, Nsight systems is what they recommend. And at a CUDA kernel level, if you want to know information about one particular kernel, there is something called Nsight Compute, right, which gives you further fine-grained statistics. Again, some things to keep in mind is the course may have been created 5-6 years ago, right? So many things that it tells may be replaced by newer utilities, because again, none of these are static, right? They're constantly improving. Vendors come up with new versions, new libraries and things like that. So it's just something for you to look up. Whenever you see such utilities, look it up and see if it is really the latest or there are newer ones. So NVProf used to be the go-to profiling tool. So it was available for all OSs, and it's able to collect statistics pertaining to multiple events and metrics. And it doesn't require the programmer to use the CUDA events API. So you can use it as a CLI tool where you say NVProf and you give it some command line options, where you say, for instance, collect all events of a particular type. You don't need to do all this fine-grained instrumentation where you add these things to the code. It will automatically collect all such events for you just by mentioning the type of events you are interested in. So those are two ways to profile. This is fine-grained profiling, where you add logs to your code based on the APIs that CUDA gives you. The other way is to use a utility and tell the utility that I'm interested in this kind of profiling or this kind of events, and it will collect details about all those events for you. And then it will also have a GUI where you can open things and look at it visually. Okay, so that's the profiling side of things. And coming back to memory, shared memory. So every SM has 64 KB on-chip memory. So again, this is what I was talking about. You can partition it as 48 shared memory plus 16 L1, or 16 shared memory and 48 L1. By default, the 48 shared memory is used. So this can also be configured using a runtime API. Okay, with that, we will move to the problem solving for today. Again, a lot of these are numericals, right? So it'll take some time. But before that, any other concepts that are not clear in week 6? What is the difference between transpose and copying? So you're asking about a typical matrix operation, or is it something particular from a lecture? Right, in the lecture. So I think there were variants of so transpose typically just refers to, in a matrix sense, just refers to, changing the rows into columns and the columns into rows. Here we were discussing, I think, coarse grained and fine grained and things like that, where there may be variants, right? These are non-standard definitions of transpose, or they may be relevant in a more limited context. And then we were trying to do some memory optimizations by, copying it in a certain way. So are you particularly interested in one of those? Because otherwise, in a general sense, I don't see a relation between just copying and transpose. So the copying is relevant in this lecture, or the access is relevant, right? So the access is relevant from a memory perspective, right? So if you access it in a certain way, let's say row wise or column wise, right? These are two typical accesses that you can do. Then it results in certain consequences, which we will see now also when we solve the problems. Things like bank conflicts, or how many global memory transactions you have, and so on. So that's why the way you access is important. So to do the same thing, to do the transpose operation, you can slightly tweak the code to access it more efficiently. So that is, if I remember right, that's what the lecture video does. So to just do the transpose operation, they are accessing elements in a particular way, but the operation itself is not changed. So in many questions, many examples that are discussed, you'll find this. The operations that are performed are kind of made complicated. For instance, you may split it into two operations, right? Where if you see the first operation, it may not be doing exactly what you want. Same for the second, but together in the combination of these two, they will be doing what you want to do. So it's like, see, when you do any of these things, right, optimizations, the first thing that you have to keep in mind is the functionality or the correctness. That should not change. So if I want to do transpose, at the end of the day, no matter how many things I split it into, it should be doing transpose. But that may be a bit difficult to understand with some of these examples because they are complicated. What you can do is just take a small example and try to work it out. That will make it clear. So that is one aspect of it. Now, given that it's functionally correct, what is the benefit of splitting something into this many operations? It basically changes your access patterns. And because you're changing these access patterns, you may be accessing data in a better way, avoiding some conflicts or having fewer transactions per warp. And as we see, as we saw before, global memory access is expensive, right? So the more you can do these optimizations without compromising on functional correctness, your program will perform better, your runtime will improve. And the good part is, of course, you still get the answer that you want. So you have to understand the correctness part of it, you have to look at, if you are breaking down one operation into two things, you have to look at those two things and convince yourself that those two things are doing the one thing that you ultimately want. After that, what is this part again is, we do it for all optimizations. We can't call it an optimization if it gives you a different answer, right? Then the second part of it is looking at the individual operations and trying to understand more about the memory access, because ultimately the goal of this week is to understand how these individual operations improve the memory access. So the other part of it is kind of the preliminary part that you need to convince yourself about, to say that okay, these two operations are still doing the end goal of what I want to do. So maybe if you still have a doubt about maybe one variant of the transpose that was discussed, you can look at it in the break and let me know the particular video. I think there were 7 or 8, right? If you can give me a video and a timestamp, I can explain the high level logic of what it's trying to do and how that helps you. What does it reduce and how it improves the memory access time. But this is a general template for all the examples that are discussed for week 6. Any other doubts? Okay, if not, we will move on to the problems. Solve maybe 3 or 4 problems and then take a break. Okay. In a GPU system, 16 consecutive floating point data values can be brought in a single global memory transaction. Again, pay attention to this. This is an assumption, right? If you remember in the previous one, we were talking about 32 aligned 4 byte words, and here we have something like 16 consecutive floating point data values. So these are all again system design things that can differ. So if a question states it, make sure to use that particular number. Consider an array A comprising floating point values and a GPU architecture with warp size 16. For the array access expression ATID, where TID equal to block IDX.x into block dimension.x plus thread IDX.x, what is the total number of global memory transactions if the total number of threads launched is 256? And you have 4 options. Take your time to think about this. You have one answer, D. Okay. D. D. Okay, we'll wait a few more seconds. Any other answers? Okay. If not, let's look at the answer. D is correct. So let's see how we get D. So remember, a global memory transaction says 16 consecutive floating point data values can be brought in one transaction. Now you have an array again of floating point values, and the warp size is 16, meaning there will be 16 threads in a warp. Now given this definition of a global memory transaction, one warp which has 16 threads will access, each thread will access this A of TID, and therefore the 16 thread accesses will be coalesced into one global memory transaction. Now what is asked is total number of global memory transactions if the total number of threads launched is this much. So you know per warp there is, so if you have one warp, you have one global memory transaction. Now how many warps do you have if the number of threads is 256? 256 by 16 is 16. So for 16 warps you will have a total of 16 global memory transactions. That's all. So what you need to pay attention to is this access expression and your warp size and your definition of a global memory transaction. That's all. Any doubts in this question? What is the significance of floating point data? So again, here I think in most of your questions it is going to be floating point only. So this 16 consecutive floating point data values, right? For instance, if there is a mismatch between this and what your array is accessing, for instance, if your global memory transaction is defined as 16 consecutive 16 into, let's say, 2 bytes or something like that, and you are trying to access something else, then how many global memory transactions one warp will need may change. So far, I haven't seen questions doing that. All of them seem to use floating point, and the global memory transaction is also defined that way. But if not, then there can be a change due to what your global memory transaction is and what the array or your input data format is. Okay. TID equal to is what? So that is just your axis expression, right? So this is your typical axis expression. If I give you a different axis expression, again, you'll see questions which do this, right? So we have lot of questions, I think, in this model, so you'll get an understanding. So why you need to pay attention to this is this defines what the threads in a warp are going to access. So this is 16 consecutive floating point data values. Now, if my threads in a warp access may be something different, that could also cause a change. If my TID itself is changed, which you will also see in some questions, then also what a warp is trying to access will change. So that's why both of these things are important. So if you remember in the lectures, you had these offset and stride, right? A of TID into something, A of TID plus something. That will also change what your warp is trying to access. And this also, the way you take this block ID x dot x, thread ID x dot x and define your TID, if you change this is also something that a programmer can do, which you'll see in some other questions, so you'll understand this also. So that also can change. That's why those are relevant. Any other doubts? Okay, so if we are doing one read and one write, total number of global memory transactions would be 32. Yes, again, depends on what is asked. So here you are specifically asked for just accessing A of TID, so it would be 16. If you are asked about a statement where you have one read and one write, then yes, answer could be 32. Okay, if there are no other doubts, we'll move to the next question. Considering the same GPU architecture configuration and number of threads in question 1, what would be the total number of global memory transactions for A of TID plus 1? Yeah, this is one of the examples I was talking about. Think about this and then let's discuss. Human answer D. Okay. D. Okay. We'll wait a few more seconds. D. Okay. Any other answers? Okay, let's take a look. So the only change here is a of tid plus 1. So when you do that, what happens? So remember, this was the offset case, right? Whenever you see a of tid plus x, you are talking about adding an offset to things. So what happens then is each warp would require two memory transactions. For example, if you consider warp 0, it would require one memory transaction to fetch elements 1 to 16, 1 to 15, and another one to fetch 16, right, which is shown here. So this part and then the rest of it. So how you do this kind of questions is, for a given warp, how many memory transactions does it take, then into total number of warps, same as last time. Only now you have to think about the offset, and you have to think about what happens because of that offset. So in this case, since it's an offset of 1, so you basically end up having one extra global memory transaction. So you have 2 accesses per warp, and you have 16 warps in all. So the answer is 32. Any doubts here? I think this is fairly easy. Let's move to the next one. Considering the same GPU architecture configuration and number of threads, what would be the total number of global memory transactions for a of tid star 2? Instead of plus, you are now looking at star. Okay, we have answers in D. I'll give you a few more seconds. Anyone else? Okay, we have one more answer. A couple more saying D. Okay, let's look at the answer. It is D. So again, remember, so all the star something is referred to as a stride, right? So in case you may be asked a question where you said what is the total number of global memory transactions with a stride of 2. So that's where you have to remember what the definition of stride and what the definition of offset are. So offset is always an addition, it's a plus something. Stride is a star something, right? So now for this TID star 2, what happens? So again, you have to think about each warp, how many transactions are needed. So each warp would still need only 2 transactions, but what it is trying to access would be different. So here in your offset case, you are accessing consecutive elements but with an offset or with a gap of 1, right? Here you will be accessing every other element. So warp 0 would fetch, some threads would fetch 0, 2, 4, 8, 10, 12, 14. All of this would be part of one memory transaction. So again, if you draw it out, you may get a better idea. Then there are other threads which are going to fetch 16, 18, 20, so on up to 30, right? And remember that this whole 0 to 15 would count as one memory transaction. The 16 to 30 would count as the second memory transaction. So even though it is star instead of plus, you still need only 2 memory transactions per warp, and you again have 16 warps, so the total number of transactions is 32, and that is D. Any doubts here? I think this is also fairly easy. So this is one set of questions which try to test your basic understanding of memory access, right? Given an expression, what is the access pattern? The next set of questions will kind of build upon this. They'll use things like tiles, and they'll use they will have an entire kernel defined, and they may redefine this TID also, which I spoke about. So yeah, we'll see that. We'll move to one more question and then maybe take a break. Considering the same GPU architecture configuration, number of threads launched in question 1, what is the total number of global memory transactions for A of TID plus 16? We have one answer C, okay. One more saying C, okay. For the others who are still working out, you can take a minute more, then we'll discuss. So again, very similar to the questions you've already done. So think about it. Instead of plus 1, we are now doing plus 16. Think of what consequences that has. C, okay. Okay, let's look at the answer. It is C16. So this is interesting, right? So even though you add an offset, it's basically your answer goes back to your option 1, which was without any offset. Why is that? Because now again, with this offset that you're adding, your axes become aligned. So if you consider warp 0, the threads 0 to 15 would be fetching 16 to 31. Now notice that all of these are in one single global memory transactions. That's what we mean when we say aligned. Therefore, that itself is enough. And for every warp, you would have one such axis. There are a total of 16 warps, so the total number of axes you need is 16, which is your option C. So whenever you have an offset, so remember there was that graph, I think, which went like this, right? It increases as you keep adding an offset, and then it decreases because suddenly a particular offset makes it aligned. So it goes back to this original value. So that's something to keep in mind. Even with a stride, could it happen with a stride? You should think about that. So any doubts here? I'll wait for a few more seconds. Okay, I think we have a little more than 10 questions today. We have maybe 12 or 13. So I think this is a good logical point to take a break. So let's take a 5-minute break from now. So it's 6:59. We'll resume at 7:04. Okay, let's move on to the second type of questions. Consider the following code snippet executing on a GPU architecture where the number of shared memory banks is 32 and the bank width is 4 bytes. So again, the code is like this. Size is defined as 32 and your function defines a tile of x and y where x and y are equal to size, and GID is calculated using the thread ID x.x star block dimension.y plus thread ID x.y. Tile of thread ID x.x thread ID x.y equal to GID. You do a sync threads. Then you have two statements where TIDX and TIDY are left blank. Out of GID equal to tile of TIDX TIDY. We'll come back to this. We'll first see what the question says. Kernel is launched with parameters 32, 32, 32, 32. Consider the last shared load operation, which is this. The accesses for this operation depends on the values of TIDX and TIDY. State whether the following statement is true or false. For TIDX equal to thread IDX dot y, TIDY equal to thread IDX dot x, shared load transactions are bank conflict free. True or false? So I'll move back to that question. So the options are just true and false. Remember only this part from this slide. TIDX is y and TIDY uses x. Now I'll move back to the code and you can spend some time looking at it and tell me if it's true or false. Are there conflicts while doing this? Take 2-3 minutes. I think this will involve a good amount of thinking. Okay, let me try that. Is this still visible? I think it's okay. Maybe a little small for some of you. Sure. So again, try to break down this question. So we'll see how to do this in one, then the rest should be easy. But two parts that you have to keep in mind is how is this tile mapped into memory, and then how are you accessing the tile, which is based on this expression, and further how you define your TIDX and TIDY. I'll give you 1 more minute. If you're not able to solve, then we'll look at the answer. Okay, maybe we'll look at the answer. This may be a little too complex. So the answer is true, but let's take a detailed look. Now, your tile is defined as size, right? This, and this is defined as 32. So first of all, you have a 32 cross 32 sized tile, and the number of banks is also given as 32. So every column of your tile will get mapped to a single bank, okay, like this. Now, this is how the tile is mapped. Second thing is how your warps, what your warps try to access. So let's look at that part. So again, warp size is not specifically mentioned here, so the assumption is taken as 32. So now your warp 0, what is it going to access? So it's going to access this TIDX, TIDY, and that is given as dot y and dot x. So for your warp 0, the axis is going to look like this, 0, 0, 0, 1 up to 0, 31. So this first element here is your thread IDX dot y, and the second element is your thread IDX dot x. So if you notice, the thread IDX dot x changes for a fixed value of thread IDX dot y. And this is true for all warps. So for warp 1, it would be 1, 0 to 131 and so on, right? So the second element changes for all of them. The first element remains the same. Now the axis is going to be like this: tile, thread IDX dot y, thread IDX dot x. And if you notice, the threads in a given warp end up accessing different columns, right? So given that you have this many banks, you end up accessing the different threads in the warp, end up accessing different banks, and that means that there is no conflict. So if all of them ended up accessing the same bank, then that means that there is a conflict. But because of the way you're writing your axis expression, dot y and then x, it ends up accessing different columns, and that makes it bank conflict free. So your statement that shared load transactions are bank conflict free is true. I'll pause here for some more time. Take a look at this. This may be a little confusing even now. You may have to spend some more time after this session trying to understand this. That's okay, right? Some of these concepts are very involved, so you need to spend time trying to understand it and draw it out and see. But again, there are variants to this question, right? Maybe 2 or 3 variants. So as we do more and more, you'll understand it better. So basically here the idea of this whole bank conflict is you want to distribute our accesses among different banks so that you get better speed again, right? Again, it's an optimization. If all of them end up accessing the same bank, then that again becomes suboptimal. It would lead to increased time. So that's what we try to do here. So by changing the axis expression somehow, we want to make sure that threads in a given warp access different columns. Okay, let's move on, then maybe you'll understand. So for the same code snippet as in question 5, state whether the following is true or false. TIDX equal to threadIDX dot x, TIDY equal to threadIDX dot y. So it's reversed here. Now the same statement, shared load transactions are bank conflict free, true or false. Think about this new access pattern for the same bank and tile and everything. Do you think there will be conflicts? Any answers? True. Okay. B false. Okay. Anyone else? So yeah, the statement is bank conflict free, meaning that there are no conflicts. Is that true or false? Any other answers? So for people who are finding this difficult, again break it down into parts, right? First, make sure you understand the question. So what is a bank? What is a conflict? And when you say conflict free versus there is a conflict, what does it mean? Like I said, it's a very simple idea, right? So if you want to access memory, if I had only one way that you could access, you're limited by that one, right? So again, what you're trying to do is to have parallel access. So you divide memory into this concept of banks, right? Maybe you have 32 of them. So you can access in parallel from all 32 of them at the same time. Now what happens if I try, even though the hardware gives me this facility, if I try to access 32 things from this bank itself, then that's a suboptimal thing that I'm doing, because I can't exploit this parallelism of access that the hardware is exposing. So what I need to do is intelligently distribute my accesses among all of these banks so that I can get that benefit of parallel access. That's all it is. So basically, let's say you have maybe 4 pathways that lead to a single classroom, right? Now if you send all your students through one path, then you are not using the other 3, and therefore the time it takes for the students to reach the class will maybe go up by 4x or maybe even worse, right? Depending on how things are. But if you use all of those 4 pathways optimally, if you divide your load across all 4 of them to the best of your abilities, then you are exploiting that parallelism, and as a result of that, you get faster time, right? So the idea is the same. So we want to make sure that there are no conflicts by making sure our access from a warp gets split across these banks. So that is the basic idea of a bank and a bank conflict. Hopefully that much is clear. I get that this kind of questions may be a little more difficult, right? Because you have to understand this access pattern and try to map it to which bank the accesses will go to. But let's see, we'll do one or two more questions and maybe you'll get the pattern or how to do it. But let's discuss the answer for this. So we have one true and one false. The answer is false. So now what happens? Your access pattern looks like this: thread idx.x and thread idx.y. So again, if you write out the access like this, right? For a warp, what the access would be, it would basically be the reverse of this. The other one would be fixed and this one would be varying. So then what happens is what I basically just said. If you have a single bank, all the threads in a warp is going to access this single column, and that is mapped to the same bank. So this is basically a scenario where there is bank conflict because of your access expression. Therefore, the statement that this shared load transaction is bank conflict free is false. Is this clear now? Any other doubts here? Again, you have a bunch of questions in this pattern, right? So if you understand one, you will understand all of them. By the same logic, if you don't understand one, you probably will not understand all of them. So if you have doubts, get it clarified. Again, the common part of it is two things, right? One, how your tile or whatever that is mapped, right? So here you will notice that one column of the tile gets mapped to a single bank. This is how the tile is stored. Once you understand that part, the second part is how the warps are going to access this tile, right? That is given to you by the access pattern, this expression. So try to break it down into that. Both these parts are important for you to understand. Any doubts here? So if you still find this very confusing, after we solve two more questions, then try to go back and look at this today. And if you don't, then we'll discuss it again in the next week, maybe one or two questions. Okay, let's solve two more questions and then we'll see if people have understood this or it's still very confusing. So same code snippet, access expression changes. TID.x is thread idx.x, TIDy is thread idx.x, both are x. Shared load transactions have bank conflicts. True or false? Try solving this now. We have done two questions, so again just this part changes. What does your axis look like? So basically you can try to pictorially visualize it, right? So in the previous question we were saying something like this: everything goes to a single bank. The one before that, everything goes to different banks, because you're basically accessing things in a given row, right? Now what does it look like? Just try to write out expressions and see, and give these values, right? Take a warp and see what elements they'd be accessing. I'll give you a minute more. A, true, okay. Any other answers? Anyone else? Okay. So can you tell me what this access pattern would look like if you have thread id x.x, thread id x.x for tid x and y? Would it access things from a single row, from a single column, something else? Anyone? That is the key to the answer, right? Once you are able to visualize that, you can easily say if there are bank conflicts or not. Okay, let's look at the answer, then maybe it will make sense. So it is false. Why is it false? So now I was talking about this visualization, right? So you have x and x. So if it's 0, it will be 0, 0. It's 1, it will be 1, 1, and so on. So you kind of end up accessing the diagonal elements. Now that you have this, it's very easy to say if there are bank conflicts or not, because you know that every column is one bank, right? So all the accesses are going to different banks. So there are no bank conflicts, and the statement that it has bank conflicts is false. That's your P. So see, a simple version of this question would be to give you some access patterns pictorially. So maybe I give you something like this. A warp is going to access this. Does it have a bank conflict? Answer is no, because each one accesses different warps, right? Another one I could give you is this, right? So make sure you understand this much. If you understand this much, it means that you understand the definition of a bank conflict, and the basic idea of it, right? Now in this question, what you need to come up with is this pictorial representation of what the axis looks like using this expression. That is all you need. So if this part is clear, then this is fine. Sorry, not described screen. Can you see my screen? Everyone else? I'm not sure what this means, but okay. So in case someone is not able to see, you can log out and log in. Typically that resolves issues. And if not, if for some reason even that doesn't work, there is a recording on YouTube, so you can always look at that, right? So yeah, hopefully that helps. So all you need to do is come up when you are describing that is not visible. I think it is based on what the others are saying. So you may have an issue. You may need to rejoin and see if things work. Are you not able to see my pointer moving? I think everyone else is able to see it. So please try rejoining. That should help you. Yeah. So as I was saying, you need to come up with this pictorial axis pattern, right? Once you do this, it's trivial. If I give you this axis pattern and then ask you, is there a conflict? I'm sure all of you will be able to say. Again, always keep the definition of a conflict in your mind. So then in this question, all you need to do is get that pictorial representation. So look at this x and x, and it's very kind of obvious that it's a diagonal element axis. Now is this clear, or does anyone still have doubts? I'll give you 30 seconds. Think about this. If you have any doubts or any trouble understanding this, let me know. And then we'll move forward, because this is the third question in this sort. I think we have one more. Okay, let's go to the next one. Is this clear to people, or is it still very, very confusing? If it is, feel free to say that, right? It's not your fault that you don't understand something. There's always a way to explain things in a more easier and clearer way. So I'll try to find that for the next session. If you don't understand, please let me know, because again, these questions that I discussed will very likely, some variation of them will turn up in your assignments and your exams, right? So these are like your template questions. So if you don't understand them, please let me know. Okay, if not, we'll move to the next one. Again, same code snippet. tidx.x is threadidx.x. tidy is equal to sz minus 1 minus threadidx.x. Again, this was 32, just for people who don't remember it. And again, you have the same statement. Shared load transactions are conflict free. You have true and false as your options. So now try to redraw this picture that I told you about. It's as simple as that. Once you draw that, you'll basically be able to figure out what the axis looks like. B, false. Okay. Anyone else? There would be conflicts. False. Okay. False. Any other answers? Okay, let's look at the answer. It's true, A. So again, let's look at why it's true, right? So again, what you can try is to come up with that pictorial representation I told you. I'll tell you a simple other way, right? So your size was 32, this becomes 31 minus threadidx.x. So in your warp, if your threadidx.x varies from 0 to 15, this tidy, will it ever take the same value for two threads? Right? If you simply look at this expression, you'll realize that it is 31 minus thread idx. So as your thread idx varies, this also varies. So it's never going to be the case that two threads access the same column, which is when you would have a bank conflict, right? So for people who said there is a bank conflict, think about why you said that, why you thought that, right? Even if you're not able to come up with this visual representation, so if you actually do that, you'll see that it is the non-principal diagonal elements that are accessed, and they also belong to different columns. So for instance, you might have something like, if you take 0, you might have 0 comma 31, you might have 1 comma 30, and so on, right? So the key part is this tidy will never be same across different threads, right? This is one way of doing it. The previous question is another way of doing it, right? Here also, if you notice, you will never have, just by the virtue that, in a warp you have different thread idx.x for all of them, and therefore your tidy will also be different, meaning that you're accessing different columns. Similarly here, your thread idx is different and you're doing a constant minus some variable. So this value will also vary as this varies. So as simple as that, you will be accessing different columns. If you're not able to come up with that pictorial representation also, it's fine. You'll simply see that this value is different across threads in the same warp. Therefore, there would be no conflicts. This is conflict free. So this statement is correct and your answer is true. Is this any clearer now? Do you understand why it's true? Any questions, any doubts? Or is it still very confusing? I'll give you another 30 seconds to look at this slide and see if you understand it. For this entire set of questions, I think many of you were confused. So please do look through the explanations once after today's session. If you still feel very confused about it, let me know, right? Okay, if not, let's go to the next question. This is, I think, a slightly different pattern. Consider the optimized shared memory implementation for matrix multiplication of A and B. So this was the tiled one that we discussed in the lectures. For a matrix of size 1024 into 1024, tile width of 64, and GPU architecture with warp size 32, what is the total number of memory accesses that would be required for only loading shared memory tiles of A and B? You have 4 options. Again, take some time to think about how many tiles you have, how many accesses per tile you have, and so on. Two 2048, okay. Anyone else? So you would break down this question as how many tiles you have and how many memory accesses you need per tile, right? The product of the two would give you the total number of memory accesses. Again, you're asked only about A and B, not C. You can take a minute more to think about this. Okay, this also looks like a slightly difficult question for everyone. Okay, let's look at the answer. So it is 4096. So let's see how to get here. So you have an n cross n matrix and a warp size of 30. This is one approach, right? And a tile width of W. The total number of memory axes for loading the shared memory tiles for A and B would be, again, like I said, the number of tiles that you need. So for A or B, it would be n divided by W, right? So again, quick recap, if your matrix is n cross n and your tile size is W cross W, you would have n by W tiles, right? And you have two matrices here, A and B, so it's 2n by W. That is your number of tiles. Now, for a given tile, the number of axes is W by 32 into W. So, this is the expression. This was there in the lecture also. So, now what we need to do is to simply use the values of W and N. So, W is given to us as 64. So, 64 by 32 into 64, and n is given as 1024. So 2 into 1024 divided by 64, which would give you 4096. But if you are wondering how you get this, right? So remember that there is this picture, right? And along one dimension, so when you are loading along a row, you would coalesce the axes. That's why it becomes W by 32. But along the column, when you are doing, it would remain W, because you can't, it basically goes to different global memory axes. So that's why that would become W by 32 into W. So this is again for the one tile part. Then you need to multiply it, or rather this is the expression I am talking about, W by 32 into W, and then into 2n by W, right? And this is your overall matrix representation. You have n as the full size and W as the tile width. So if you use this formula, you get C. So two ways: either you remember the formula and you simply substitute the values, or from first principles you think about how many tiles there are per matrix, multiply that with 2, and how many memory axes you need per tile, right? That's all it is. So both of those will give you the same answer, C, 4096. Is this clear now? The good part about doing it logically is, in case something's changed, right? Maybe your warp size changes, right? Then you may end up blindly using the formula, or you may realize that something has changed, but you won't know how to change the formula accordingly. So if you do it from first principles, even if something changes in the question, for instance, the warp size changes, then you will quickly be able to derive this. That may be something you can think about, right? If warp size changes, what changes here? It may be obvious given that it's 32 in both places, but think about why that changes. Why is it this that changes when your warp size changes? Things like that. So I always recommend learning to derive this from first principles. Thinking about your tile axis in a matrix, and thinking about how many tiles there are and how many axes you have per tile. Again, this also may be a little complicated, so spend some time looking at it and see if you understand it better. Any doubts here? Okay, if not, let's move to the next question. Consider the following code snippet where on an architecture where width of L1 cache line is 64 bytes, width of L2 is 16 bytes, warp size is 16. As we know, global memory access width equal to warp into 4 bytes, which is 64 bytes in this case. So you have a mem access function that's like this: tidx equal to block idx.x into block dimension.x plus thread idx.x. out of TIDX equal to in of TIDX. Assume that you have 256 threads being launched. Size of both these arrays are 256. What is the total number of L1 writes to L2 cache given this program snippet during the entire lifetime of the kernel? You have four options: 16, 32, 64, 128. Any answers? Again, very different question from. I think this was briefly mentioned in one of those profiling activities, right? When you saw a higher memory access, as to why it is higher, but you may not remember that part. Okay, we have one answer saying A, which is 16. Okay. A, okay. Let's look at the answer. Anyone else before we do that? No? Okay. If not, we'll look at it. So it's actually C64. So let's see why that is. So now your warp size is given to you as 16, right? So first of all, this is going to be your, for this axis expression, you can easily coalesce axes across a warp, right? So one warp, so even though you have 256 threads being launched, the total number of memory transactions that you have is 256 divided by 16, which is your warp size, which is 16, or simply one memory transaction per warp. But now you're asked about the number of L1 writes to L2, right? Now the L1 cache line is 64 bytes and the L2 cache line is 16 bytes. So now even though your L1 cache line is 64 bytes, you will end up doing 4 writes for each transaction of 64 bytes. So L1, if L1 has 64 bytes as the cache line size, and you're writing to something that has a smaller cache line size. So basically, to compensate for that smaller cache line size, you're going to need to do 4 rights per 64 bytes. Therefore, there is this factor of 4 that comes in. So all of you said 16, I think. But because of the cache line size difference, there is this magnification in number of writes, which goes to 64. That's what was discussed in the lectures also, right? So yeah, the option is C. And you can try thinking about what happens in the reverse case. If you want, we can discuss that in the next class. This is just because of the cache line size difference. Any doubts here? Okay, if not, I think we have two more questions, but I think all of these are a little too complicated, so I don't want to overwhelm you. We will take these two questions in the next class. But what I noticed was still question 5 or 6, all of you were able to get it, but the last 5 questions were a little complicated for most of you. So please take this time to go through them and maybe even solve your week 6 assignment questions. And if you find a particular category of questions difficult, please let me know, and we'll maybe discuss an easier version of one of those questions and then go to the leftover 2 questions, right? We'll do that next week. So, any other doubts or questions? We still have, I think, 7 minutes left. So, any other doubts or questions? Okay, I'll stay on the call for 1 or 2 minutes. So those of you who have any questions can stay back and type it out on chat. If not, thank you so much for joining and see you next week. Thanks for keeping it interactive again. Feel free to drop off. How can you access on YouTube? So there's a sheet that's, I think, shared with all of you. I'll just put it here again. You're welcome. So this has the YouTube link for every week. I typically upload it within a day of the live session, so feel free to check it out. Any other questions? Okay, if not, thank you so much and see you next week.